In this video, I will derive the general solution of an E&M wave propagating in an arbitrary waveguide. I will consider a waveguide which is uniform in the z direction but arbitrary in x and y. This means that the wave will be a plane wave in the z direction, but will have a dependence in x and y which can be complicated or very different. So the task is to find a general expression for this type of waveguide. The z dependence is simply going to be given by the plane wave solution exponential of ikz. The frequency dependence is simply going to be given by I omega t. The same is true for the magnetic field. We now consider two cases. The first case will involve a wave which is the transverse magnetic wave, where the magnetic field is always perpendicular to the direction of propagation, in this case z. The idea here is to find a general expression which ensures that B is always going to be perpendicular to Z. And this involves using a trick. The trick is to write a general solution or trial solution, which we call an ansatz, in a very general form. And in this case, it's going to be given by the curl of a function of x and y in the z direction. The curl of that function will ensure that the magnetic field will always be perpendicular to z. Let's see whether this is really the case. So I'm going to look at the expression of the curl of this general function psi of x and y multiplied by the component, the unit vector z. This is simply given by the determinant of my dx, dy, and dz derivatives and the component z, the component x and y I0, and then I just have the unit vectors in x, y, and z. Taking the determinant of this, we immediately see that the first term of the determinant is just dy psi times x, which is this term here, and the second term is basically dx psi times y, which is the term here. And we immediately see that there's no term which involves the z unit vector. So this ensures that this vector is always going to be perpendicular to the z component. So the z component of this vector is basically always 0, and that's why this vector will always be perpendicular to z. So going back to our expression, we have B always perpendicular to z. So the next step is to identify what is psi of x and y. In order to find psi of x and y, we're going to plug in this magnetic field into the Maxwell's equations. One of the Maxwell's equations involves the curl of B. And it turns out that the curl of B is going to be given by this expression here. And this is simply obtained by taking the curl of this B here, and this is done in the next page, where we have this expression again of B, for which we're going to take the curl. So to take the curl, we can write it in a term in form of a determinant like above, And we're going to look at the terms of that determinant. So the first term is going to be, let's using the color blue, it's going to involve the derivative in x times this term here times z, and that's simply going to be this term, the first term in z. The second term in z is going to involve the derivative in y times the derivative in y of psi exponential of ikz minus omega t, and times z. And so this one is simply this term here over here. Another term is going to be the derivative in z multiplied by the derivative in x of psi x exponential of ikz minus omega t times the unit vector x. And this is the term over down here. Finally, the last term is the derivative in z multiplied by the derivative in x psi exponential of ikz times y, which is the term down here. We can now look at the first term in red, and we see that there's a derivative in z, which will only be applied on the exponential of kz, which is the only dependent on z, and that's why the ik will come up in front, and we're left with just the derivative in x times psi. The same happens here, where we have the derivative in z, which is going to take out the k down here and put it down here. And so combining these expressions, we basically get what we had before. So we have this can be written as basically the Laplacians of psi, which is thus the double derivative of x, which is here, plus the derivative in y, is basically this one here, multiplying psi. And then we have the other term in kx here. So these term here, this dx times x direction x is one term of the gradient, and the other one is dy times the y here is another term of the gradient, and so these together give basically the gradient of x and y, which is down here. So what we have shown is that the curl of b is equal to this expression down here. So let's go back to the Truesdale expression here, and this is exactly what we have written down here. So the curl of b is equal to this expression. So we now have the expression of curl of b, and then what we want to see is if the Maxwell equations remain valid with this expression. So let's take one of Maxwell's equations, which is the curl of h equals to b dot, where b is equal to mu h. So what we can do now, we can simply evaluate d, which is the integral over time of the curl of h. But the curl of h, that's nothing else. The h is equal to b over mu, so this is the integral over time of the curl of b divided by mu. So we have to take the integral over time of this expression, dt, which basically gives us a 1 over omega, 1 over minus I omega. And so we're going to multiply this expression by I on top, and that's why we get, multiplying this by I because of this I omega t, what we get is 1 over mu omega multiplied by the same term as above, except that we had multiplied by I. So this is now the expression for d. So what do we do with this? So we have this d equals to all this, and we want to see whether this expression for d is consistent with Maxwell equation. To do that, we can take the divergence of d, which is equal to rho f, the free charge, but if we assume that the free charge is 0, then the divergence of d should be 0. So what we have to show is that this divergence of d times d is indeed equal to 0. Is that true? Well, let's have a look. So here I have the expression for d, which we had before, and I'm going to take the divergence of this. So let's express d in its components. So the gradient of psi is simply the derivative in x times psi in the x direction plus the derivative in y of psi in the y direction multiplied by k, and the whole thing is multiplied by 1 over mu omega. The Laplacian of psi is just dx squared plus dy squared times psi in the z direction times I times the exponential of I kz minus omega t. So by taking the divergence, the first term I have is basically I have to take the derivative of my x component, which is dx psi. So I have the dx times dx psi, which is my first component of my divergence. The second component is dy times dy psi. And then the z component is dx squared plus dy squared, and on that one I have to apply the derivative in z. So the third component for my divergence is equal to this. So these are my three derivatives for my divergence, and I already see that this is again just this plus this is again my Laplacian. Here I have also my Laplacian, but then I have a derivative in z which only applies itself on the exponential of kz here, so that takes the k out in front, and so I'm left over an ik. So ik times I is minus k, so I get minus k Laplacians of psi, and so what I have is k Laplacian of psi minus k Laplacian of psi, which is equal to 0. So indeed, the divergence of d is equal to 0. So let's go back to Maxwell's equation. We have basically shown that using this expression for b, applying the curl on it gives us d dot. Taking the integral of d dot, we get d, which is this expression here. Then we take the divergence of that, and we show that this is equal to 0. So now let's look at the next Maxwell equation, and this is simply divergence of b equals to 0. So what I have to do, I have to take the expression of b, take the divergence. So basically take the divergence. What I need to do is to take the divergence of that expression here. And I will not show it here, but it's basically following a similar procedure as for the divergence of d. It is quite straightforward to show that this is 0 too. I use 3 Maxwell equations, this one, and this one. And we have shown that all 3 are valid. So one is left, and this is actually the most interesting one. So let's look at the last equation of Maxwell. So the fourth Maxwell equation is given by the curl of E is equal to minus B dot. We have B, which is up here, and now we simply have to take the time derivative of B here. So what's the time derivative of B? Well, we're only going to get basically an I omega coming out up front. And that's basically this I omega down here. And then we just have the expression of B, which is this here, times the curl, which we have shown before is simply equal, can be expressed in this simple form here. So now we want to have a look at this term here, the curl of E. And again, the curl of E is taking the curl of D, but D is equal to epsilon E, so this is basically equal to epsilon E, so the curl of E is basically 1 over epsilon times the curl of D, which is given by this expression here, which shows this 1 over epsilon coming from this 1 over epsilon over there. So again, like before, we can we can obtain this expression simply by doing it by component to component, and the derivation is very similar to what we did for the taking like the divergence of D or the curl of B. So let's look at this expression more closely. What we can take the omega on the other side and all the constants on the other side, and then what we have is dy psi of x here, and we have here dy of the Laplacian minus k squared psi of x here, whereas here we have dx of psi times y, and again the Laplacian minus k squared psi of y here. So if this is equal to this term here, then this term will also be equal to this term here. So the only thing we have to ensure is that psi multiplied by these constant is equal to the Laplacian minus k squared times psi. And this is exactly what this expression is here. We've put all the constants on the left, multiplied by psi is equal, there's a minus sign here, minus the Laplacian minus k squared times psi. And this is really the final expression, which basically has to be true in order for all 4 of Maxwell equations to remain valid. So as long as what is in green is true, we know that all these 4 Maxwell equations will be valid. And then we have the expression for B and the expression for D, which is thus proportional to the expression for the electric field. So using this expression for this displacement field, we can also write an expression for the electric field, where we simply have replaced this operator, the Laplacians of psi, which is basically here and here. We basically have just plugged in delta psi, which is equal to omega squared epsilon mu psi plus k squared, and we have replaced that into this Laplacian of psi in order to get the expression inside the square brackets. So what we have obtained is an expression for E, for the electric field, expressed in terms of this function of psi, where we have shown that this is consistent with all four Maxwell equations, and we have, in order to find psi basically has to be a solution also of this differential equation. So the bottom line is that if we find the solution of this differential equation for psi, then we can write an expression for the electric field as just a function of this psi in this form. And that electric field will be a solution of a transverse magnetic wave where B is always perpendicular to Z in a waveguide along the Z direction. So the next step is to look at case number 2, which is basically the case where the electric field is now perpendicular to Z and not the magnetic field. And this is the transverse electric field. We can do something which is very similar to the transverse magnetic case. The only difference in this case is that instead of using B as a curl of this function psi, we have to define E as the curl of that function psi. This again will ensure that E is perpendicular to Z, and then we do the same calculations as before, and we get an expression for B, which is very similar to the expression of E obtained in the transverse magnetic field. So we have found the solution for the two cases of a transverse electric field, electromagnetic wave, and a transverse magnetic electromagnetic wave. For general waveguide, which is uniform in the Z direction. And the important equation to solve is basically this differential equation, which is basically just a Laplacians evaluated on the boundary, where the waveguide determines the boundary condition. And this will be the next topic of this video. So summarizing, this is what we have. We need to find a function psi of x and y, which is a solution of this differential equation. And then for the TM case, we can write B as the curl of Z times psi x of y exponential of ikz. And for the T case, we write E is equal to the curl of Z times psi exponential ikz, and then E is this, and then B is this in the T case. So this, again, this is true for any waveguide which is uniform in the Z direction. So the next step is to find the solution of this differential equation here. Basically to find psi. So let's apply this result to an actual waveguide. So let's consider the following waveguide, where we have some contour C, and which defines basically the limit of the waveguide, and it's uniform in the z direction, which is the direction of propagation of the wave. Now, let's assume that this contour C is a perfect metal. Then this implies that the electric field in the z direction. So if I would write, so along that metal, that electric field E component z has to be equal to 0 along that contour. So this is basically the condition Ez is equal to 0 along the contour C. And in order to get Ez equals 0 along C, we have to impose the following condition, which is psi is equal to z along the contour. So let's go back to the expressions of C and for the TM wave. So imagine now that indeed psi is equal to 0, then what we have is that if psi is 0 along the contour, that means that this expression psi here, which is basically the component in the z direction, this one is only in the direction of x and y, so the only z component term is this term here. So if psi equals to 0, then that means that Ez will necessarily be 0. So psi equals 0 at the contour will basically lead to the fact that Ez is going to be equal to 0. And so this is basically this expression we have here. So t equals 0 along C will ensure that Ez is equal around C. So then, in order to find the expression for the electric field, we basically have to solve the following two equations. We have the Laplacian of psi equals to this omega squared epsilon mu minus k squared of psi. And that's this differential equation we had before. But we have to make sure, we have to introduce this boundary condition of psi equals to 0 whenever xy is on the contour C. So along this contour C, we want psi equals to 0. And this is true only for the TM case. So again, all is needed is to have psi equals to 0 on the contour, which will imply that Ez is going to be 0, so there's no electric field parallel to the conductor at the conductor, which is what is a requirement for a good conductor, for perfect metal. And so if by solving this, we get an expression for psi, and then we plug that back into the expression for E, so we can get then an expression for the electric field in terms of psi, and then also an expression for the magnetic field. This is true for the TM case. Now, for the T case, which we have here, what we want is that the electric field is always perpendicular to Z. So automatically E parallel to Z is going to be always 0. So we already see that we're not the same conditions as we had for the TM case. So what happens to the T case? Well, let's go back to the expression. For the TM we had psi has to be equal to 0. Well, for the TE case, what we actually have is that the condition which replaces the one for the TM is going to be that n times the gradient of psi is equal to 0 along the contour C, where n is basically a vector which is perpendicular to the surface of that contour, or of the line of that contour. And in this case, if we do this, then it is possible to show that indeed this will lead to the correct expression of TE, which basically tells us that we want the electric field to be always perpendicular to the propagation, which is in this case Z. So by imposing this condition on psi, again we have to solve the differential equation of the Laplacian of psi equals this omega squared epsilon mu minus k squared psi, but at the same time imposing the boundary condition where n gradient of psi equals to 0 along the boundary of C. And this will give us the solution, the TE solution for the electric field and magnetic field. To show that this indeed leads to the transverse electric field is somewhat similar to what we did for the TM case, and I will not show that here, but it is easy to verify using the expressions we had before. So, concluding this section, we basically derived a general expression for the solution of an E&M wave propagating in a waveguide which is uniform in the z direction but can take on an arbitrary shape in x and y. The only thing we have to solve is this Laplacian in psi, which is only a two-dimensional Laplacian. Again, this is only, and psi is only a function of x and y, and they have to respect this boundary condition for the t case and this boundary condition for the tm case. Once we have psi, we can use the expressions shown earlier, like here. So once we have psi, we can get an expression for the electric field, for the t case in this case, and for the tm case, an expression here. And then we also get automatically the electric field expression here and the magnetic field expression for the t case here. So this is a very general way, basically a very general solution to the waveguide problem of a uniform waveguide in the z direction. Thank you for watching.